All right, so our second speaker is Taro Spirig, and he's going to talk about a quantum unique games conjecture. Take it away.
All right, thanks. So today I'm going to talk about a quantum unique games conjecture. This is based on joint work with Hamoon and Mousavi. So I'd like to first start by talking about the main motivation for our work. And as a disclaimer, I might use some words that you're not familiar with, but later on I'll define the main definitions for our work. So the main motivation for our work is the question, how hard is it to compute or approximate the quantum value of non-local games? And we know now by MIP historical RE that this is undecidable in general. But apart from that, we know very little. In contrast, the same question for the classical value of non-local games has been studied intensively. So it's a natural question to ask if we can lift some of the classical knowledge that we have about the classical value to understand the complexity of the quantum value of non-local games. But the problem is that working with the quantum value of non-local games, all right, no worries. Working with the quantum value of non-local games is really hard. So instead, we can work with a similar, a simpler yet as expressive restriction of the quantum value. That is the so-called synchronous quantum value of non-local games. And we can also do an additional conceptual simplification by instead of looking at games, we can think about optimization problems called constraint satisfaction problems. So as you can see here, the classical value of non-local games corresponds to classical CSPs, and the synchronous quantum value of non-local games will correspond to non-commutative CSPs. Okay. And so now we can then ask the same question as before. Can we then lift all of the knowledge that we have about classical CSPs to understand non-commutative CSPs? Okay. But it turns out that this question is also pretty hard to answer. In fact, we know that the non-commutative setting, non-commutative CSP, just behaves very differently from classical CSPs. So in this talk, I'm going to consider instead quantum CSPs. That's something that we define. We're going to see that in this setting, we can actually quite easily lift classical CSP techniques to this quantum CSP technique. I should note here that when I say quantum CSP here, I mean actually in the non-local game point of view, it corresponds to oracularizable synchronous quantum strategies, if you're familiar with the terminology. So in summary, we started at the very left here, trying to understand the complexity of the quantum value of non-local games. But that's really hard to work with, so we've done a bunch of simplification to arrive here. And I'm going to talk about this relationship here between classical CSPs and quantum CSPs. And more precisely, the technical results that we show is that first, we can show that a quantum analog of the PCP theorem follows directly from MIP historical RE. We propose a quantum unique games conjecture. And assuming that this conjecture holds, we're able to show tight hardness results, tight hardness of approximation results for problems like Tulin and max cut. Okay. So in short, it seems that for quantum CSPs, we can lift basically some of the main results about classical CSPs to this quantum setting. I should note here that the second bullet point is particularly interesting because non-commutatively, we know that actually an E-game conjecture does not hold by a beautiful result by Kempe, Regev, and Toner. Also, when I say tight hardness results here, it's really like a direct translation. So we're really taking the classical statement, and we replace classical value by quantum value, and NP by RE. Moreover, I really want to stress, especially because of the previous talk, that I'm going to use the word quantum quite a lot. When I say quantum CSP here, it's not the local Hamiltonian problems as the previous talk, but I'm really thinking about more of this CSP thing, more like a game version of it, right? Okay, so what are quantum CSPs? So first, I'll introduce classical CSPs with the example of max cut. So an instance of max cut is a simple graph, and the goal is to color the vertices of this graph with two different colors, +1 or -1, to maximize the fraction of cut edges. Okay? And an edge is said to be cut if the color associated to the vertices are different. Okay, so here the edge ij is a cut edge because the color of I is green and of j is blue, right? Okay. And the dotted line here goes through all cut edges. Okay. So mathematically, how does that look? So we're like interested in the optimal value here, or we're just going to call the classical value here. And it's the maximum over all possible classical assignments, right? All possible coloring. We're taking the fraction over all edges, and this is the indicator function, whether the edge is cut or not. So this thing here is equal to 0 when xi is equal to xj, and it's equal to 1 when they're different, right? When xi, xj is equal to -1. Now, a non-commutative CSP or non-commutative max cut is a direct generalization of this classical max cut to the operator setting. So basically now, instead of assigning colors to vertices, we're going to assign unitary Hermitian operators to every vertex. Okay, so now here we assign xi, which is a unitary operator too. And then the value of the non-commutative value of max cut is really a direct generalization where instead of having just a product of xi times xj, now we have a product of the unitary operators, and we're taking the normalized trace to get a number out. Okay. And I should note that it seems a bit arbitrary, this definition here, but this really, as I said, corresponds to actually a non-local game, like the value of like the synchronous value of non-local games. And also, so you can also see it as a sort of probabilistic assignment to a coloring of this graph here. But I don't really have enough time to explain this relationship. And finally, quantum max cut is the same thing as non-commutative max cut with the additional requirement that we are imposing this commutation relation here. So xi, xj in the operator assignment commute with one another if I and j forms an edge. Okay, so here the operator xi here and xj have to commute with one another. Because I and j share an edge. Okay. And in terms of terminology, like the reason why we call this quantum CSP is really because this requirement of this commutation requirement comes from simultaneous measurability. That's been also used previously in the literature, for example, in this work by Helton et al. All right, so now in the rest of the talk, I want to kind of explain what are the results that we get. And for that, I need to tell you a bit more about the classical CSP landscape, because that's what we want to lift right in this quantum CSP case. So classically, we know that many problems are NP-hard. For example, 3-SAT, 3XOR, or a max cut. But interestingly, we also have efficient ways to approximate those problems, right? So we have the Gurmans-Williamson algorithm, for example, that approximates the value of max cut with a ratio of 0.878. And 0.878 here is an approximation ratio. It means that for any instance of max cut, we know that the algorithm, the Gurmans-Williamson algorithm, will output an assignment whose value is, roughly speaking, bigger than 90% of the optimal value. Okay. But you see here that like, if instead of 0.878 we had 1, then we would efficiently solve an NP-hard problem, so this shouldn't be possible. So it's kind of a natural question to ask, like, what is this best constant possible here? Is it 0.878 or is it 1? What is it exactly? And to answer this question, classically, the starting point is the hardness of approximating a problem called label cover. And that's the content of the PCP theorem. Label cover is a pretty similar problem to max cut in the sense that it's also about coloring a graph. But this time, this graph is a bipartite graph here. And the alphabet, so like the number of colors is bigger than just 2. It's over an alphabet m here. And instead of just like coloring to maximize the number of cut edges, now we want to maximize the number of satisfied constraints. And the constraints are given by maps, which are associated to every edge. Okay. And as I said, and I should note that actually, as for max cut, we can similarly define like non-commutative and quantum generalization of this, right? So instead of having colors, we would assign operators of a certain order, unitary operators of a certain order to every vertex. And so the PCP theorem states that actually this problem is extremely hard in the sense that for every constant delta bigger than 0, there is a large enough alphabet such that approximating label cover within this constant delta is NP hard. Okay. So this is really, really hard. And then the idea then to show, to answer the question that I asked previously, for example, for max cut, the idea is then to reduce the hardness of the PCP theorem, which is this really, really hard problem, to the hardness of other problems, such as max cut. And so a reduction here is really just this idea that we want a reduction from a problem A to B is just an efficient map that maps instances of the first problem to the second problem, such that if it's hard to approximate the first problem within some ratio, then it is NP hard to approximate the second problem within some other ratio, say gamma. So what we want here is to have, for example, A being label cover, B is in max cut. We can let delta being anything because of the PCP theorem. And then we want gamma to be 0.878. So that would be the dream scenario. Okay. And this idea actually works really well. For example, for certain CSPs, for example, 3 XOR is a 3 CSP, where the PCP theorem reduces exactly to the hardness of approximation of 3 XOR, meaning it's hard to approximate 3 XOR within a ratio bigger than a half, and which is a tied result proved by Hostad in 2001. However, actually, the dream scenario doesn't work for max cut. Actually, that's a general problem with 2 CSPs. So we need then to reduce actually from a sort of tweaked version of the PCP theorem, which is the unique games conjecture. Okay. And so the unique games conjecture is really the same thing as the PCP theorem, only that instead of approximating label cover, we're talking about the approximation of unique label cover. And unique label cover differs from label cover in the way that every map, like I showed you, constraints are defined by maps, which are associated to edges. And these maps have to be bijective in a unique label cover instance. And if we assume that this is indeed hard, then we actually get hardness of approximation of max cut, and actually hardness of approximation of all 2 CSPs. So it's an extremely useful and powerful tool. And we really get 0.878 on the nose, which is really quite surprising. So quantumly, what do we know then? So it turns out that actually by MIP star equal RE, we also have a quantum analog of the PCP theorem. So really here, instead of having label cover the classical value, I'm looking at the quantum value of the label cover, so this operator assignments. And it directly follows from MIP star equal RE that this is RE hard to approximate within any constant. And as in the classical case, this result here can be reduced to to quantum 3 XOR hardness, actually. So this is a result by O'Donnell and Yuan, and an unpublished result from last year, where they kind of showed it from a slightly different perspective, but basically they show that it is RE hard to approximate the quantum value of 3 XOR within a ratio bigger than a half. And so what we did is to extend this. We wanted to know if the unique games conjecture and all of these other beautiful results could also hold in this quantum setting. So we can actually state such a unique games conjecture. So it's exactly the same thing as the unique games conjecture classically, but we replace the classical value by the quantum value here. From this, we were able to quantize other classical results quite easily, actually. So we're able to show two-lin hardness of approximation and max cut hardness of approximation. I should note here, though, that there's a slight subtlety here. It's we need a statement a little bit, a slightly different statement of the unique games conjecture than the one stated here to show this hardness of approximation. All right, so what are the proof ideas, very roughly? So classically, reductions are pretty complicated to come up with, right? So we need to actually rely to construct those maps that map instances of one problem to the other. You need to rely on error correcting codes, and you need to test those codes in sort of smart ways. For example, if you're familiar with the BLR test or noise stability, those are the tests that we use for 3 XOR and this one for max cut hardness. And then the analysis of these reductions are based on Boolean Fourier analysis. And the quantizations, or how do we transfer those results into this quantum setting? Well, actually, this is quite easy in some sense, because the reductions, we kind of keep the same reduction, but the analysis needs to be quantized, and for this quantization, we need two key ingredients. The first one is that Boolean Fourier analysis lifts to operator Fourier analysis, in which case, classical probabilistic assignments become POVMs, and then we can sort of massage them to make them into PVMs. And PVMs correspond to unitaries, so observables. So you can then, that's the way we get operator assignments for quantum CSVs. And then the second ingredient is the most important, is the commutativity. So now we finally use the fact that we're not in the non-commutative setting, but we're in this quantum setting, where we have some additional commutation between the operators. And with this commutation, we leverage it to simultaneously diagonalize some of the operators, and then we can actually rely on the classical analysis for the eigenfunction of these operators. Okay. And so, for example, we really don't need to show any sort of operator generalization of the majority stabilist theorem, which is like a very deep result in Boolean Fourier analysis that is crucial for the hardness of approximation of max cut. So we really don't need to show anything crazy here. It's really relatively easy. All right, so let me conclude now. So, right, in this talk, I focused on this double arrow here. As I said, we have quite a few evidence that shows that we can easily lift classical CSP techniques to the quantum CSP, setting. But it's a natural question then to ask, is this really a general phenomenon? Can we really easily quantize all classical reductions to this quantum setting? It seems that whenever we have Fourier analysis, this seems to be quite easily done, but is this really always the case or not? Related to this question, can we actually show a weaker version of MIP star equal RE? As I said, MIP star equal RE directly implies the quantum analog of the PCP theorem, but would it be possible to actually show it directly by quantizing, for example, Dinur's PCP theorem? That would be particularly interesting because this was really hard. MIP star equal RE is famously a really hard result. It'd be interesting if in this setting, actually really this phenomenon holds and we can really just easily quantize Dinur's PCP theorem. Also, it'd be interesting if perhaps this could show an alternative and easier resolution of Kahn's embedding problem. I'm not really sure about that, but yeah. Also, it'd be really truly interesting if we could lift similar ideas to the non-commutative setting to show hardness of approximation for non-commutative problems. Actually, the next talk will be about an approximation ratio for the non-commutative analog of max 3 cut. And it'd be interesting if we could actually show and lift similar ideas to show hardness for those kind of problems. Finally, it'd be really good to know actually which games are oracularizable in general. So this is maybe a bit technical, but there are certain games which have this property that, it's a sort of transformation that you can do. It'd be interesting if oracularizability actually behaves pretty similarly to synchronicity. That's a bit technical, but I think this would be really interesting, especially in the imperfect regime. We don't really know if that's the case or not. All right, thank you for your attention.
Maybe we have time for a couple of questions.
For bullet point number 3.
Yeah.
Did you try, for this working this non-commutative, did you try super dense calling and teleportation for other quantum games that worked out pretty well? So we can do super dense teleportation and to somewhat transform certain quantum games into at least classical quantum games. So this might be something close to your, just try it. It's very nice.
Okay, interesting. No, I actually am not familiar with these kind of results, so maybe we could talk about it afterwards. I'd be very interested to hear more about it. Thanks.
Thank you for your talk. I just wanted to clarify. So, you didn't like prove the quantum UGC. You
Yeah.
proposed a conjecture,
Yeah, absolutely.
and you could propose it's RE hard
Yeah.
based on the MIP star equals RE, and then you proved that then the RE hardness of quantum lin2, a 2-lin, and quantum
Absolutely.
max cut. Okay.
Absolutely.
And it may turn out maybe this is not RE hard, but maybe it's just QMA hard or something. But
Yeah, absolutely. No, totally. Yeah. It was just really about like the techniques. It seems that really we can lift all of these techniques to the quantum setting. Yeah, that's what we're interested in.
but even if it's only like QCMA hard or something like unlikely, but maybe, then the results would still carry over, right?
Yeah, absolutely. No, the reductions hold, but yeah, we still need to prove the quantum unigame conjecture. But what's interesting is that really because of this tight relationship between like QGC and UGC, or like the quantum setting and the classical setting, we're also kind of wondering if like perhaps it'd be easier. I mean, it seems somehow that like studying this quantum setting, we kind of how can I say, like in the classical setting, there's kind of like a lot of freedom to play with, and in these reductions, actually we're kind of using a lot of the freedom that was left in the proofs. We kind of had to use all of this freedom. So it seems a little bit like maybe this quantum setting is also pointing towards what needs to be done or something like this. So it could be interesting if there is this, we could learn even more about the classical setting by studying this quantum setting. That would be really interesting as well. Yeah.
Do you know if the classical implies the quantum or vice versa?
No, that's an open question, of course. Yeah.
Okay. Thank you.
Yeah, thank you very much for the nice talk. I don't understand why to define a quantum CSP problem, you only need the commutation constraint and not like a tensorial structure as usual. Like.
Right. So I'm not sure if you're familiar with like synchronous strategies.
No.
Okay. So maybe that's why. So really, that's why it's kind of a simplification. So we're kind of, this is not directly the way it would look like for strategy for a game, because we're already kind of one step ahead of a sort of simplification, where a synchronous strategy is one where you're forcing the state to be a maximally entangled state, and you're only looking at one set of PVMs. Okay? So both Alice and Bob are using this set of PVMs. And because of the maximally entangled state, the tensor product, you're taking the tensor product of Alice's operators and Bob's operators. And because of the entangled state, you can actually push it on the other side. I'm not sure if you know this trick, but you can. Okay. Yeah, maybe I can explain it to you a little bit later. Yeah. Sorry? Yeah, exactly. Yeah, that's true. Yeah.
Okay, thank you.
Hey, I'm just wondering if you had like if you knew the hardness of MIPCO with the constant gap, can you do a similar analysis?
That's a very good question. I think actually it should hold, yeah, but I haven't really thought about it super thoroughly, but yeah, I think it should be good, yeah.
Thanks.
Any other questions? All right. If not, then let's thank the speaker again.